Moving on from smog. So greenhouse gases, we've termed them greenhouse gases because they are the reason that it's keeping the heat in and the planet's warming up, just kind of like a greenhouse. So what's happening is these greenhouse gases, which are in the atmosphere, see these guys, greenhouse gases in the atmosphere, they absorb what's called long wave radiation. Okay, and this is like all the short waves were reacted and didn't get into the atmosphere, or if they did, we kind of like absorb them and we use them and things like that. The long wave radiation is the stuff that got through the atmosphere, but then it gets trapped. Okay, so long wave radiation then gets kind of absorbed because of the atmosphere. And when I say because of the atmosphere, I mean because of all the molecules in the atmosphere. Most planets don't have an atmosphere, or at least not much of an atmosphere like Earth does. We have a much more abundant atmosphere than Mars, for example. So before I kind of walk through this picture here, the reason that this whole radiation thing is causing us to heat up or to maintain temperature anyway, is because of those molecules. So on Mars, the temp actually drops like 100 degrees Kelvin or Celsius because they don't have an atmosphere or anything to absorb that heat. So Mars, the temp decreases by about 100 K. That's a lot at night because it doesn't have an atmosphere, it doesn't have molecules to absorb that radiation. At night, because no atmosphere. Okay, we need our atmosphere. It's very important to keep us warm. Obviously, if our temperatures dropped 100 degrees every night, we would have a lot of problems. So what's really going on? And I like this picture because it's numbered. It kind of walks you through what's going on with which light waves are getting through, how much energy is getting through. Now, we're not going to calculate any of that. We're just kind of generally look at this. But essentially, we've got like solar radiation, of course, coming from the sun. So that's step number one. The solar radiation is coming into the earth from the sun, of course. Now, some of it gets absorbed because we've got clouds and stuff here. Okay. And that actually makes a big difference. Clouds can be extremely helpful. So the clouds absorb some. Clouds absorb some. So not all of it gets down to the earth. Okay, so that was like step one and step two, some of it gets absorbed. Now, once it gets down here, okay, some of it doesn't get through the atmosphere. So if you look at number 3, some of the solar radiation is reflected by the atmosphere. Okay, so some of it, like it just can't get through those molecules. It doesn't cause a reaction or something. Sometimes it does cause a reaction, like we've talked about photodissociation and photoionization, but some of it just gets ejected back out. Okay. Now, if you go to number 4, solar energy is absorbed by the Earth's surface and warms it. Okay, this is kind of what we were talking about Mars-wise, and like we need our Earth to stay warm. So some of it gets absorbed down here. Okay, and then we've got number 5. Some of the infrared radiation is absorbed and re-emitted by the greenhouse gas molecules. Okay, this is why greenhouse gases are important. But can cause more warming than what we want. So they absorb and then re-emit different wavelengths of molecules. Okay, so this is what we're going to talk about, this kind of step right here. Okay, now what also happens, some of the infrared radiation passes through the atmosphere and is lost to space. So some of it goes, some of it is gone, but a lot of it kind of stays down here. So you can see this arrow, some goes out, some stays down here. Some goes out, some stays down here. And then the surface ends up gaining more heat, and infrared radiation is emitted again, and it's this whole cycle. Now, it's an important cycle, like I said, but it's this whole cycle. Notice down here, he said when it's absorbed and emitted back, that's the long wave infrared radiation that we're talking about. So we're really talking about these steps over here, like 4, 5, and 6. Okay. And like I said, it's really complicated. This is a very delicate balance of what's happening in the atmosphere. So we're going to try to break it down as much as we can, but like what's going on with this absorption and re-emission of heat. Okay. So greenhouse gases, what are they? All of these right here are greenhouse gases, and you've probably heard of all of them. Of course, carbon dioxide, that's the one that everybody's like, this is so bad. We blame carbon dioxide because we've made a ton of carbon dioxide. Water, believe it or not, is also a greenhouse gas, like the water in the atmosphere, like water vapor. also absorbs and re-emits radiation. Methane, you might have heard of methane being an issue. Everybody talks about cows producing methane, and it's actually because they chew their cud so much that they produce a lot of methane. So beef, farmers who have beef and cattle actually produce a lot of that methane. Nitric oxide, we talked about where that comes from, and ozone, we talked about where that comes from. So all of these are greenhouse gases. Some of them are more abundant than others. So believe it or not, the one that is the biggest greenhouse gas, the one who does the most absorbing and radiation, is water. Water vapor actually does about 90% of the greenhouse gas reactions. Now, there's nothing we can do about the water. The water is going to be in the atmosphere. It's part of the air, and it's not because we're putting it there. It is natural. Okay, so this is actually our primary greenhouse gas. You might have thought it was carbon dioxide. It's not. Carbon dioxide is secondary, and methane is up there too. But we kind of attack carbon dioxide because, well, we're the ones producing carbon dioxide. We're not producing so much water that it's a problem. That's there anyway. So a lot of the time you see like this graph here that shows our CO2 emissions over the years. And yes, this is alarming, right? We've gone from the 1900s to when we started like the Industrial Revolution and all of that up to where we are now. Very, very high amounts of carbon dioxide. And you might have noticed it dipped a little bit because of the pandemic and people weren't going as many places, and that was natural to happen. But over the years, it's actually gone up about 35%, in the last 40 years. Okay, and this is because of humans, Okay, so carbon dioxide is a problem. I'm not saying that it's not. It's just not the biggest contributor to greenhouse gases. Okay, so what do these do? Why do these affect the temperature? If you look at the next page, they are absorbance spectrums for these greenhouse gases. Okay, so things that absorb and emit radiation. So I like this chart here. This is actually stuff that you would look at if you take like organic chemistry. You can see which types of waves are absorbed and emitted by which molecules, also inorganic and PChem. But the atmosphere, this is all the stuff that gets absorbed in our atmosphere. And then if you look at each individual graph, you can see which waves they tend to absorb. So I'm just going to look at water here for a minute, and you can see water absorbs a lot of waves down here. Okay, so water likes to absorb, these are the infrared waves. Okay, and it absorbs a lot. That's why it's the biggest contributor to greenhouse gases. So H2O absorbs, I'm going to put it the best, because it absorbs a lot of those waves. Okay, carbon dioxide also, notice not as much, but also in the IR. Both of these absorb IR radiation. Now, if you're looking over here, you might have noticed this peak over here. Ozone tends to absorb UV radiation, which we also talked about on Tuesday. That's a good thing. We want it to absorb the UV radiation. So if you look at these graphs, you can kind of see which wavelengths are absorbed by which greenhouse gases, and they get absorbed and emitted, and that's how we kind of keep the energy where it is. Okay. Now I want to talk a little bit about how complex this is. So a lot of people will latch on and be like, well, CO2 is going up, temperature is going to go up, or it's going to die. But it's a very delicate balance of a lot of factors. So there's a lot of projections out there. Like I know we've all heard about global climate change and the Earth's temperature increasing. They, quote unquote, lots of climate scientists, they've predicted that our temperature could rise by possibly 3 degrees Celsius. That's a lot to get the temperature of our Earth to rise 3 degrees Celsius. That would actually melt all of the ice caps. So they predicted that it could rise about 3 degrees Celsius. They said by the end of the century. So we got a while. By the end of the century.
How long is that? And how much is that in Fahrenheit?
I don't know. Somebody want to do that one for me? Let's see. 3 times 37.4. No, that can't be right. That's not right. Alexa, how many degrees in Fahrenheit is 3 degrees Celsius?
3 degrees Celsius equals 37.4.
Oh, I was right, 37.4. So yeah, that's quite a bit. And like I said, that would melt the ice caps, and that would be obviously potentially bad because then we'd be underwater. Well, we wouldn't, but the other ends of the United States would. So yeah, that's a lot. Now that's a very high prediction, and that's based on just the things that make the temperature go up. Now, there are also things that make the temperature go down. Like I said, this is a delicate balance. We don't really know 100% what's going to happen until it happens, unfortunately, because as the temperature increases, it changes the weather. So we also get increased cloud cover. And when we have more cloud cover, then we don't have as much radiation coming all the way through. So that would be something that counterbalances the temperature going up because of greenhouse gases. Okay. Another thing is that the carbon dioxide relationship, a lot of people compare, right, that carbon dioxide increasing relationship to the temperature increasing relationship. And they say that it's exponential. And if you actually look at the numbers, it's more of a logarithmic relationship. Okay, so more logarithmic with temperature. Okay, not exponential. Okay, so what I'm really getting at is all of these things and more. It's a delicate balance. Okay, there's a lot of moving parts. And yes, climate scientists do take all of these things into consideration, but it's really hard to predict when you have all of these things changing. Yeah, I think you're right, Troy. It was just saying the straight temperature, the temperature change is going to be different. Yeah, that's not going to be 37. 5 sounds about right. Thank you. So yeah, yes, carbon dioxide increasing is a huge problem and one that we can work on controlling. But like I said, there's so many things going on. It's really hard to predict what's going on or what will happen. So we've seen a lot of predictions, temperature going up, all of those things. You kind of have to take them with a grain of salt because there are so many things happening that, like I said, it could increase cloud cover and then we won't have as much, as many rays coming through, that type of thing. So other forces that drive climate change, and actually the main forces that drive climate change are going to be the sun and the ocean, which of course covers most of our world. So the sun, you probably already know this, that it has cycles, right? It has cycles of sunspots. So it actually produces different amounts of energy at different times of the year. So its energy output varies. Every 11 years with sunspot activity. That's what this graph is of. I know I cut off the axes and the title, sorry about that. But that's essentially what's happening is we get peaks and valleys of how much energy is coming from the sun. So that drives climate change as well. And the ocean cycles drive climate change. So oceans, different parts of the ocean change temperature a lot. You've probably heard of El Nino. When we're in an El Nino year or a La Nina year, the temperatures change quite a bit, the winds change quite a bit, and so does the climate. So in the ocean, La Nina and El Nino affect the ocean temps. And honestly, so does ocean acidification, which I'm not even really going to talk about today, but that can cause problems as well. So we can actually predict the weather a lot more based on these specific cycles than what's going on with carbon dioxide and all of the greenhouse gases. So these are actually better predictors for precipitation. So we use these to predict precipitation, temperature, hurricane frequency, okay, all of these things are affected in our fun, delicate balance that is our world. I'm going to move on to the oceans here. So once you guys get this down, I'm going to scroll.
So I actually looked it up when you did the Celsius thing, the 3 degrees Celsius.
Yeah, what is it?
So I looked up the average Earth temperature as of 2011. I guess it was 14.4 degrees Fahrenheit.
Right.
And an increase to about 17 Celsius would mean about a 5.4 degree Fahrenheit change.
Yes, so that's how much it has changed.
That's how much it's estimated to change by the end of the century. It's
Oh, to change by
5.4
end of
degrees.
century. Awesome, thank you.
Yeah.
Yeah, so what I asked Alexa, it told me what that temperature was in Celsius.
Right.
instead of
That I realized
change.
that. I thought
Sorry about
37
that.
was really high.
That would be insane. Yes. So I appreciate that. Thank you.
Yep.
Yeah. So 5 degrees may not sound like much, right? But that would be enough to melt the ice caps and cause all kinds of problems. So thank you for looking that up. I appreciate it.